Hello everyone and welcome to Control Engineering and Control Theory tutorials. In this tutorial, we will answer one very important question. We will provide the answer to the question of stability of a third-order transfer function or a third-order system. That is, the problem is, what are the conditions that the constants k, a3, a2, a1, and a0 have to satisfy such that this system is asymptotically stable? Let's solve this problem. Okay, let's talk about facts. First of all, this constant k, which can also be even a polynomial, does not influence stability. This is very important to keep in mind. That is, k doesn't influence stability, forget about it. Now, locations of zeros of this polynomial determine the stability properties. That is, the zeros of these polynomials are actually called the poles of the system, and they determine the stability properties. Then, third fact, this is a very important necessary condition. And if this condition is not satisfied, you immediately know that the system cannot be asymptotically stable. So let's state this condition. This condition states that all the coefficients, that is, this coefficient, this coefficient, this coefficient, and this coefficient must be positive. Or equivalently, all the coefficients must be negative. That is, all the coefficients must have the same sign and none of the coefficients should be equal to 0. Don't be confused about these two conditions. Namely, this condition is basically saying that all the coefficients should be positive, and then I said equivalently all the coefficients must be negative. For example, if all the coefficients are negative, you can simply multiply this part by -1, and you can make all the coefficients to be positive. So it doesn't matter. How do you do that, and how can you see that? You always determine the stability by actually computing the roots of this polynomial. a3s to the power 3 plus a2s to the power 2 plus a1s plus a0. And if this is equal to 0, and nothing will change if you multiply this by -1. That is this equation. Let me write it down. Oops, I made an error here. Should have minus here, a2s squared plus, actually minus again, a1s minus a0. That is, this equation is mathematically equivalent to this equation, and you can see that by multiplying any of these equations by -1. You will obtain the same equation. And consequently, you will see that the positivity of all the coefficients is equivalent to negativity of all coefficients from the perspective of this necessary condition. To derive the main condition for the asymptotic stability of this system, we need to use the famous Routh-Hurwitz stability test. This test first constructs a table, and on the basis of the coefficients in that table, we will determine the stability properties. This table is constructed like this. The rows are associated with the power of s. We will have the first row associated with the s to the power 3, the second row associated with s to the power 2, the third row associated with s, and the last row will be associated with s to the power 0. Then, the entries in this first row are actually the coefficients a3, then we skip a2, a1. So we have a3 over here, then over here we will have a1, and some people add here 0, and I will add 0 over here. However, we will not need a 0. Now, the entries of the second row are a2, then we skip a1, and then we have a0. So we have a2 over here, then we skipped a1, and we have a0. And over here, people add a 0. Okay. All other rows of this Routh-Hurwitz table are constructed from the first two rows in a recursive manner. And let me explain that. The entry over here is actually constructed like this. It's a ratio of, in the numerator, we will have A2. Then, over here, I will have this determinant. I will simply take this column and will put it over here. Then I will take this column and I will put it over here. And in that way, I will construct this matrix and I will compute this determinant. And over here, I need to add the minus sign. This is how this entry is constructed. Similarly, the entry over here is constructed like this. I will take, again, a ratio. In the numerator, I will have A2. Then, in the numerator, I will have A3, A2, that is this column, and this 0 column over here. And that's it. Over here, we just fill in a 0. Now, let's compute these elements over here. Obviously, this entry will be equal to 0. How about this entry over here? Let's compute it over here, and let's see what we will get. In the denominator, I will have simply A2. In the numerator, I will have minus. And if we evaluate this determinant, we will have A3 multiplying A0 minus, let's nicely write this minus, A1 multiplying A2. Consequently, this entry becomes, in the denominator we have A2, and in the numerator we will have A1 multiplying A0 minus, or actually I have to correct this, it is A1 multiplying A2 minus A3 multiplying A0. And that's it. Simple as that. Over here, for clarity, I raised the determinant and I replaced the determinant by the computed entry as well as by this 0 over here. Okay, next we need to construct these two entries, that is the entries in the last row. Again, the principle is the same. So what is the principle? The principle goes like this. We'll have a ratio. I will call this entry over here as C0, and here in the denominator over here I will have C0. Again, we use the same principle. We take this column and we take this column, we compute the determinant with the minus sign. So let's write it here. We will have A2, right? Then we'll have C0, which is this element over here. Then we will have A0, this A0 over here. We will have 0 over here. Then we close the determinant and we have a minus sign. Okay, how about this entry over here? Again, in the denominator, we will have C0. What we will have in the numerator? In the numerator, we will have again determinant. We take this column, A2, C0, 0, 0, and here we have a minus sign. Obviously, this entry will be 0 again. However, let's compute this entry. Let's do it over here. This entry becomes, we have in the denominator C0, and we have A2 multiplying 0 is actually 0. So we have a minus sign, A2 multiplying 0, which is 0, minus A0 multiplying C0. Okay, good. So this part is 0, so we have simply A0 multiplying C0 divided by C0. C0 and C0 can be cancelled, so I have A0. And that's it. Over here, I erase the determinant for the clarity, and in this row, we need to write A0, and we need to write 0 over here and 0 over here. Okay, good. The Routh-Hurwitz stability test, or the stability theorem, tells us that if all the coefficients in the first column, that is in this column of the Routh-Hurwitz stability table, are positive, then the system is asymptotically stable. This is very important. Again, we first compute this table, then we check the sign of these coefficients in the first column, and if all the coefficients are positive, then the system is asymptotically stable. Okay, let's do that. However, before we do that, we have to remember the first necessary condition, and this is how we verify the stability. The first necessary condition is that A3, A2, A1, and A0 should be positive. Okay, we keep in mind this, and we assume that this is the case. And the second condition follows from the Routh-Hurwitz stability test. It states that A3 should be positive, A2 should be positive, then this coefficient C0 should be positive. Let's write it down here. This is A1 multiplying A2 minus A3 multiplying A0 divided by A2 should be positive, and finally A0 should be positive. Note that if you assume that this is the case, then this is satisfied, this is satisfied, and this is satisfied. Now, the condition for asymptotic stability is that C0 is positive. Since A2 is positive, by this assumption, then we have that the condition for stability, or better to say for asymptotic stability, is this thing. And this is the fundamental result for the stability of the third order systems. That is, the product of these inner coefficients should be larger than the product of the outer coefficients. And you can see that by transforming this equation like this, or this inequality, better to say, like this. Okay, so again, the condition for stability of this transfer function, or more generally of the third order system, is that all the coefficients are positive, and in addition, it is required that this inequality is satisfied. This inequality means that the product of the inner terms should be larger than the product of the outer terms, or the outer coefficients. And that's it. That's all for today. Thanks for watching.